Welcome. This video is an introduction to the semantics of LP. The semantics of LP specifies the meaning of symbols of our formal language. From this perspective, we can divide the vocabulary of LP into three different types. First, there are the symbols that receive a constant interpretation. That includes all our logical connectives. Because these symbols receive a constant interpretation, they're often called logical constants. Then there are symbols in our vocabulary that receive a variable interpretation that changes from one context to another, and those are, of course, our sentence letters. And we call these sentence letters. But in other treatments, they are also known as propositional variables because each one of them can mean a different proposition. Okay, we're not going to use the language of propositional variables, but just in case you ever hear that somewhere, that's the same thing as our sentence letters. And then there are symbols in our vocabulary, exactly two of them, that we use just for grouping. Those are just the parentheses, and we don't have to worry about what those mean because they don't have any meaning. We just use them to disambiguate expressions. So now, what we're going to focus on is how to specify the meaning of the logical connectives. And before we do that, we need two key things. We need to focus on one key concept, and then we need one key assumption. So our key concept, our key semantic concept that we're going to use throughout the entire course is the concept of a truth value. And it's really difficult to define it. And so what we typically say is a truth value is just the value of truth for a given proposition or sentence. We're going to work with a system that has exactly two truth values, T and F. And our truth values are always going to be T and F. And we take them to represent true and false. If we were working in computer science, we might take 1 to be true and 0 to be false, but we're not going to do that. And we need a key concept that we're going to use. I'm sorry, not a key concept. We already did the key concept. We need a key assumption. And this assumption is central to the kind of logic that we're building here. We talked about it in the first day of class. Our key assumption is sometimes called the principle of bivalence. And the principle of bivalence just says that any sentence of LP is determinately either true or false. So that means that any given sentence in our formal language is going to have one of our two truth values. We're also going to see that our logical connectives are truth functional. And this is a really important concept as well. What that means is that if we have a compound sentence, the truth value of the compound sentence is uniquely determined by the truth value of its atomic components. So the truth value of a compound sentence is uniquely determined by the truth values of its atomic components. And the language of function here is not accidental. These are our logical connectives are truth functions in the mathematical sense of the word. They're mapping us from one set to another. Okay, so now what we can do is, with this key concept and this key assumption, and remembering that our logical connectives are truth functional, actually display the truth functions that our logical connectives codify. And in doing that, we're going to specify indirectly exactly what each one of our logical connectives means. So let's start with negation. The way we specify the meaning of our logical connectives is by building what is traditionally called a canonical truth table. We start, in the case of negation, by thinking about an arbitrary slip, an arbitrary sentence of LP that I'm designating here with the script letter P, and we think about all the possible truth values that that sentence can have. Well, we already know we're working with a two-valued system of logic, so script P can be either true or false. And then by definition, we take it that neg script P is defined by exactly these resulting values when we put the negation in front of the P. So if P is true, neg P is false. If P is false, then neg P is true. And that, believe it or not, completely specifies what we mean by neg P. And you can think of very simple examples to convince yourself, and I encourage you to do that. Let's move on to the next one, which is conjunction. Now, conjunction is a sentence of LP that has as its main logical connective the wedge. So we want to know what truth values are we going to assign to the sentence P and Q when we canvass all of the logical possibilities for the truth values that P can have and the truth values that Q can have. Now, we already know that these are going to be, that the P and Q sentence is a function of the truth values of P and the truth values of Q. And what we want to do is write down all the logically possible combinations of assigning true and false to P independently of assigning true and false to Q. And the way to do that is to follow a pattern so that we don't leave out any possible combinations. And the pattern is we're going to write down two T's followed by two F's as we go down the page. And then for the Q, we're just going to alternate TF, TF. And that covers all the bases, right? We have all possible ways of assigning T and F independently to P and Q. And now what we want to capture is the meaning of and. And so if you think of a very, very simple example, such as something like Beto wears socks and sandals. Okay, then I could write that out as saying Beto wears socks and Beto wears sandals. And if I wanted to symbolize this, maybe I could do K and D, right, for socks and sandals. And of course, it's pretty straightforward to see that this sentence, K and D, the entire sentence is only ever going to be true when both K is true and D is true. And so likewise, in general, for any arbitrary sentence script P and any arbitrary sentence script Q, P and Q is only ever going to be true when both are true. So it's going to be true in the first row and false on every other row. And notice that I've done something here that you can always do with a function, as you know from your algebra course a long time ago, right? I can specify a function by telling you the output values given the input values. I can think of the pair TT as an input pair, and then the output that the function gives you is T, and I can just give you a list, just like if I was multiplying numbers or something like that. Or I can tell you a rule. The rule is P and Q is true only when both P is true and Q is true. And sometimes you can use the rule to help you remember what the truth table is like. And you basically have to commit these canonical truth tables to memory so you can build more complicated truth tables. Let's move on to disjunction. A disjunction, we've already seen, is a sentence of the form P or Q. And we want to specify the truth value of P or Q as a function of the truth values of P and the truth values of Q. And again, you could think of this as a kind of input-output pairs, okay? So again, we're going to do TTFF and then alternate to make sure we cover all our bases. And now we're going to think about how do we capture the meaning of saying P or Q. And I want to work through this one a little bit more slowly because there's a little bit of a subtlety with or that isn't present with the and. So let's think of an example that'll motivate how we're going to fill out this truth table. My example is this. Suppose somebody were to say to you, to take this course, you must have completed either Run 101 or Run 102. What do they mean, right, in terms of the requirements? What is the requirement here? So suppose we let A be, I have completed Run 101, and we let B say, I have completed Run 102. So what is the requirement if I try to write it down in my symbolic notation? Well, it looks like what this person is telling me is that I can take the course if either A or B. Right? If I've either completed Run 101 or have completed Run 102, then I can take this course. Awesome. Let's think this through a little bit more carefully and ask, under what conditions is the sentence A or B true? Okay, so now I'm going to do a separate little truth table here that's going to motivate our general one. And I want to canvas all the logical possibilities. And I say, for example, right, remember A is I have completed Run 101. So if it's true that I'm going to look at the second row here. If it's true that I have completed Run 101, but false that I've completed Run 102, have I satisfied the requirements to take the course? And the answer is yes, because the person said you have to have completed either 101 or 102. So it's going to be true in the second row. What about in the third row? What if I've taken 102 and have completed it? That means B is true, but I have not completed 101. Well, the advisor told me that I could take this course if I've completed either 101 or 102. I completed 102, so I'm good. It's true that I have satisfied the requirement that I've completed either 101 or 102. Let's move on to the last row. In the last row, suppose that I have not taken either 101 or 102, then obviously I haven't satisfied the requirement, so it's false here. A or B is false. It's not true that I have completed Run 101 or Run 102 if I haven't completed either one of them. Now, the important bit here is this first row. What if I've taken both of them, right? Suppose I took 101 last spring and I took Run 102 in the summer. Well, obviously I satisfy the requirement because the requirement doesn't rule out the possibility that I could have completed both Run 101 and Run 102. So the or in this case is true when they're both true. And that's the canonical definition of the V, okay? So for the V, the truth table that defines it has 3 T's and an F. Now you'll notice there's a T when they're both true. Okay. This meaning of or we usually call the inclusive or. It's inclusive because it includes the possibility that both are true. And that's how we define the meaning of this symbol. When you're symbolizing, like in your exercises, the safest thing to assume is that any or that you're symbolizing is inclusive. But there may be times when what someone is telling you doesn't include the possibility that both of the pieces of the or are true. The pieces of the or, by the way, are called disjuncts. So let's think of an example where we would not think that this is what or means. So how about this one? Suppose you go to the pharmacist and the pharmacist says, either your prescription is filled or you have to see your doctor. And let's think about how we might symbolize this. Okay, so R is your prescription is filled, and D, you have to see your doctor. Well, if you think about it, what the pharmacist probably meant is that either your prescription is filled or you have to see your doctor, but not both, right? It's not both the case that your prescription is going to be filled and you have to see your doctor. So this is an example where it would probably be incorrect to symbolize this as R or D, because that leaves open the possibility that both R is true and D is true. And that's very unlikely to be what the pharmacist meant. So how do we write down what the pharmacist meant? Because the pharmacist did not mean R or D. So let's not leave that on there. Let's get rid of that. So how do we write this down? How do we symbolize what the pharmacist said? Well, I already said it. We paraphrase by thinking about what did the pharmacist mean? And what I said is that what he probably meant was that all of this is true, right? Either your prescription is filled or you have to see your doctor. And then I said, but not both. Now we have an inroads to thinking about how to symbolize this, because this says R or D, but not both. Both what? Both both R and D. So the pharmacist is telling me R or D, but not both R and D. Did I say that right? R or D, but not both R and D. And so now I can put the entire sentence into symbols, and it says R or D and not both R and D. So even though in English, we just have exactly the same thing we had before, either or, right? Before we had an example with either or, right? You have either taken run 101 or you have taken run 102. In that case, because of the context, we could tell that it was an inclusive or. Here, exactly the same pair of words, either or, is actually, because of the context, an exclusive or. Okay, so this is an example of an exclusive or. And if you've ever done anything with computers, you know that in computer science, they do this. That's the XOR. Okay. And you can build out the truth table for it. I haven't shown you how to build out truth tables for it, but basically you can anticipate how this is going to look, right? Because you already know. Oops, sorry, I'm going to do this the way we're going to eventually do it. When we make a truth table, we always put the letters in alphabetical order. You can ask me about that later. But we already know what the truth table is going to look like because we know this part. We've covered canvassing all the logical possibilities. And we know what we mean. When we say one or the other, but not both, we mean that this entire sentence, so beneath its main logical connective, it's going to be true if one of them is true or the other is true, but that's it. And so we can anticipate that later when we learn how to make truth tables, this is going to be the column beneath the main logical connective. All right, I hope you enjoyed this video. Don't forget to submit your video worksheet, and I'll see you all in class.